Mars may look close in images and animations, but in reality it is separated from Earth by one of the most extreme distances humans have ever attempted to cross. This distance is not fixed or simple. Earth and Mars orbit the Sun at different speeds and along different paths, which means the distance between them is constantly changing. At their closest approach, Mars can be about 56 million kilometers away. At their farthest, the distance grows to more than 400 million kilometers. Even the closest distance is so vast that it challenges every limit of human space travel. To understand why this distance is such a serious obstacle, it helps to compare it with missions we have already completed. The Moon, humanity's farthest successful crewed destination, is only about 384,000 kilometers away. Astronauts reached it in roughly 3 days. Mars, at its closest, is more than 140 times farther than the Moon. This alone should make it clear that traveling to Mars is not just a slightly harder version of going to the Moon. It is an entirely different category of challenge. Physics plays a central role here. Spacecraft cannot simply fly straight to Mars at high speed like a jet airplane. In space, fuel is extremely limited, and accelerating continuously is not possible with current propulsion technology. Instead, spacecraft follow carefully calculated curved paths called transfer orbits. The most efficient route is known as a Hohmann transfer orbit, which uses the least amount of energy but takes a long time. Using this method, a one-way trip to Mars typically takes between 6 and 9 months. This long travel time is not a design choice. It is a physical necessity. Going faster would require exponentially more fuel, making the spacecraft too heavy to launch. Every kilogram added means more fuel, which adds more weight, which then requires even more fuel. This creates a vicious cycle that current rockets cannot overcome. As a result, astronauts would be trapped inside a spacecraft for hundreds of days, drifting through deep space with no possibility of rescue. The distance also limits when missions can happen. Earth and Mars must be aligned in a specific way for the journey to be efficient. This alignment, called a launch window, occurs roughly once every 26 months. If something goes wrong and a launch is missed, crews must wait more than 2 years for the next opportunity. Once on Mars, astronauts would also have to wait months, or even more than a year, for Earth and Mars to realign for a return trip. This turns a Mars mission into a commitment of several years, not just months. During this extended travel time, astronauts are exposed to the harshest environment humans have ever faced. Deep space is not empty or peaceful. It is filled with high-energy particles traveling at near light speed. The longer the journey, the greater the exposure to this radiation. Unlike short missions in Earth orbit, where astronauts are partially protected by Earth's magnetic field, a Mars-bound crew would be completely unshielded for months at a time. The distance makes this exposure unavoidable. The time factor also creates a communication problem. Signals travel at the speed of light, which sounds fast, but over interplanetary distances it becomes painfully slow. At its closest, a message from Earth to Mars takes about 3 minutes one way. At its farthest, it can take over 20 minutes. This means real-time conversation is impossible. In an emergency, astronauts cannot receive immediate help or instructions. Every decision must be made alone, with incomplete information, increasing the risk of fatal mistakes. Distance also magnifies the consequences of failure. On the International Space Station, if something breaks, replacement parts can be sent within days, and astronauts can return to Earth quickly if needed. On a Mars mission, this safety net does not exist. If a critical system fails halfway to Mars, there is no turning back and no external help. The spacecraft cannot simply stop or wait. It must continue forward, carrying astronauts who may already be running out of air, water, or power. Travel time also affects basic human needs. Food, water, oxygen, and medical supplies must all be carried from Earth. For a journey lasting years, this means enormous amounts of supplies. Recycling systems help, but no system is perfectly reliable over such long durations. A small leak, contamination, or mechanical failure could slowly become deadly. The longer the travel time, the more likely it is that something will go wrong. Another major issue is human health during prolonged travel. Months of weightlessness cause serious physical changes, including bone loss, muscle weakening, and changes to the cardiovascular system. The longer astronauts remain in space, the more severe these effects become. By the time they reach Mars, their bodies may already be too weak to function effectively in a hostile environment. Distance turns Mars into a destination where astronauts may arrive already physically compromised. The immense distance also removes flexibility. Missions to the Moon allowed astronauts to abort and return home quickly if something went wrong. Mars missions do not offer this option. Once the spacecraft is on its path, physics locks it in. Turning around requires enormous energy that the spacecraft simply does not have. This means astronauts must accept from the beginning that they are committed to the journey, no matter what happens. In the end, the distance to Mars is not just a number measured in kilometers. It represents time, isolation, risk, and irreversible commitment. It stretches human technology, biology, and psychology to their breaking points. Until propulsion systems, life, support reliability, and human health protections are radically transformed, the immense distance and travel time to Mars remain one of the strongest reasons why sending humans there is far more unrealistic than it appears. Mars is not just far away. It is distant in a way that challenges the very limits of what humans can survive. Human biology evolved under very specific conditions that have remained mostly unchanged for millions of years. Earth provides gravity, a thick atmosphere, a protective magnetic field, regular day-night cycles, and a stable environment for food, sleep, and movement. Long-duration space travel removes almost all of these conditions at once. When humans leave Earth for extended periods, especially for missions lasting months or years, the human body does not adapt smoothly. Instead, it begins to deteriorate in ways that are not fully reversible, revealing a deep conflict between human biology and deep space travel. One of the most immediate problems is the absence of gravity. On Earth, gravity constantly pulls on our bodies, shaping our bones, muscles, and internal systems. In space, microgravity removes this constant force. As a result, muscles no longer need to support body weight and begin to weaken rapidly. Even with daily exercise, astronauts lose muscle mass and strength at a significant rate. Bones suffer even more. Bone tissue is continuously rebuilt on Earth in response to stress, but in microgravity that stress disappears. Astronauts lose bone density at a rate similar to severe osteoporosis, increasing the risk of fractures that may never fully heal. The cardiovascular system also struggles in space. On Earth, the heart works against gravity to pump blood upward. In microgravity, blood shifts toward the head and chest, causing facial swelling and increased pressure inside the skull. Over time, the heart weakens because it no longer needs to work as hard. When astronauts return to gravity, many experience dizziness, fainting, and difficulty standing. On a long mission to Mars, these changes would occur before arrival, potentially leaving astronauts physically weakened at the exact moment they need to perform demanding tasks in a hostile environment. Vision problems are another serious biological issue. Many astronauts experience changes in eyesight after long stays in space, a condition linked to increased pressure inside the skull. The shape of the eye can change, damaging vision permanently. For a Mars mission, clear vision is not optional. It is critical for survival, navigation, repairs, and scientific work. Permanent vision damage during it could end a mission before it truly begins. The immune system also behaves unpredictably in space. Studies show that immune cells become less effective, and latent viruses that normally remain inactive can reactivate. This means astronauts are more vulnerable to infections, even from microbes already present in their own bodies. In deep space, with no hospital, limited medical supplies, and delayed communication with Earth, even a minor illness could become life-threatening. Radiation exposure creates one of the most severe biological conflicts. Earth's magnetic field shields us from high-energy cosmic radiation. In deep space, this protection disappears. Astronauts are exposed to radiation that can damage DNA, increase cancer risk, harm the nervous system, and accelerate aging. Unlike many risks, radiation damage accumulates silently over time. A Mars mission would expose astronauts to radiation levels far beyond current safety limits, and there is no proven way to fully protect the human body from this threat without making spacecraft impractically heavy. The brain itself may be affected by long-duration space travel. Research suggests that cosmic radiation can damage brain cells, affecting memory, decision-making, and emotional regulation. These are not minor issues. In a mission where every decision matters and mistakes can be fatal, even small cognitive impairments can have catastrophic consequences. Human biology did not evolve to function under constant radiation bombardment while isolated from Earth. Sleep and mental health are also deeply tied to biology. Humans rely on natural light cycles to regulate sleep, hormones, and mood. In space, artificial lighting and irregular schedules disrupt circadian rhythms. Astronauts often experience insomnia, fatigue, and reduced alertness. Over months or years, chronic sleep disruption can lead to depression, anxiety, impaired judgment, and weakened immunity. These effects are magnified when combined with confinement, monotony, and extreme isolation. Reproduction and long-term health present another unresolved problem. We do not know how human reproductive systems respond to long-term microgravity and radiation. Studies suggest that radiation can damage reproductive cells and increase the risk of birth defects. This raises serious questions about the long-term survival of humans beyond Earth. A species that cannot safely reproduce in an environment cannot truly live there. Nutrition also becomes a biological challenge. Food in space must be processed, preserved, and stored for long periods. Over time, nutrients degrade and diet variety becomes limited. This can lead to deficiencies that affect bone health, muscle function, immunity, and mental well-being. On Earth, fresh food and medical intervention can correct these issues. In deep space, biological decline may continue unchecked. Another critical issue is healing and injury recovery. On Earth, gravity, blood flow, and normal immune responses support healing. In space, wounds heal more slowly, and infections are harder to control. A broken bone, internal injury, or surgical emergency during a Mars mission could be impossible to treat effectively. Human biology simply was not designed for trauma management in microgravity. Perhaps most importantly, adaptation has limits. While the human body can adjust to short-term spaceflight, long-duration missions push beyond those limits. Many biological changes observed in astronauts do not fully reverse after returning to Earth. A Mars mission would expose humans to these stresses for unprecedented lengths of time, possibly causing permanent damage before they even reach their destination. In the conflict between human biology and long-duration space travel, biology is not winning. Every system in the human body, from bones and muscles to the brain and immune system, depends on Earth-like conditions. Remove those conditions for too long, and the body begins to fail. Until science can fundamentally protect or redesign how the human body functions in space, long-duration travel remains not just difficult, but biologically unnatural. Beyond Earth's atmosphere and magnetic field lies an invisible but extremely dangerous threat: radiation. On Earth, life is protected by powerful natural shields that block or deflect most harmful radiation coming from space. Once humans leave this protective bubble, they are exposed to levels of radiation that human biology was never designed to endure. This makes radiation one of the most serious and least solvable problems in deep space travel, especially for long missions such as a journey to Mars. Radiation in space comes mainly from two sources. The first is solar radiation, which includes energetic particles released by the sun, especially during solar flares and coronal mass ejections. The second, and more dangerous source, is galactic cosmic radiation. These are high-energy particles originating outside our solar system, often from exploding stars. They travel at nearly the speed of light and can pass through most materials, including metal spacecraft walls and human tissue. On Earth, we are largely unaware of this constant radiation bombardment because our planet's magnetic field deflects many charged particles, while the thick atmosphere absorbs the rest. Together, these systems act like a powerful shield. In low Earth orbit, astronauts aboard the International Space Station are still partially protected by this magnetic field. Even then, they receive higher radiation doses than people on the ground. Once a spacecraft travels beyond Earth's magnetic influence, that protection disappears almost entirely. During a long-duration mission, such as a trip to Mars, astronauts would spend months or even years exposed to this radiation nonstop. Unlike brief exposures during medical procedures, space radiation is chronic and cumulative. Every day adds to the total dose absorbed by the body. Over time, this radiation damages cells, breaks DNA strands, and interferes with the body's ability to repair itself. One of the most well-known risks of radiation exposure is cancer. High-energy particles can alter DNA in ways that cause cells to grow uncontrollably. The risk increases with both dose and time, meaning a long mission dramatically raises the chances of developing cancer later in life. What makes space radiation especially dangerous is that galactic cosmic rays are far more energetic than most radiation encountered on Earth, making their biological damage more severe and harder to predict. Radiation does not only cause cancer, it can also damage the nervous system. Studies suggest that exposure to cosmic radiation may impair memory, learning, and decision-making. These effects are especially concerning for deep space missions, where astronauts must operate complex systems, respond to emergencies, and make critical decisions without immediate help from Earth. Even small cognitive impairments can lead to catastrophic outcomes in space. The heart and blood vessels are also vulnerable. Radiation can damage the lining of blood vessels, increasing the risk of cardiovascular disease. This type of damage may not be immediately noticeable, but can develop silently over time. A Mars mission could expose astronauts to radiation levels that significantly raise their risk of heart problems, both during the mission and long after they return. Another major concern is acute radiation exposure from solar storms. The Sun occasionally releases massive bursts of energetic particles that can reach astronauts with little warning. On Earth, these events are mostly harmless because of our magnetic field and atmosphere. In deep space, a strong solar storm could deliver a potentially lethal dose of radiation in a short period. While spacecraft could include small shielded areas for emergencies, predicting and fully protecting against such events remains extremely difficult. Shielding itself presents a major engineering challenge. Radiation protection requires dense materials, but adding thick shielding dramatically increases spacecraft weight. More weight means more fuel, higher costs, and technical limits that current rockets cannot easily overcome. Even with heavy shielding, some types of radiation, especially high-energy cosmic rays, can penetrate deeply and even create secondary radiation when they collide with shielding materials, sometimes making the problem worse instead of better. Mars offers little relief from radiation once astronauts arrive. Unlike Earth, Mars has a very weak magnetic field and a thin atmosphere. This means its surface is still exposed to significant radiation levels. Measurements from robotic missions show that radiation on Mars is much higher than on Earth, making long-term human presence extremely dangerous. Living on the surface would expose astronauts to continuous radiation, while living underground would require extensive construction and resources that are currently impractical. Radiation also affects reproduction and genetics. Damage to reproductive cells can increase the risk of infertility or genetic mutations. This raises serious concerns about long-term human survival beyond Earth. A species cannot thrive in an environment where its genetic material is constantly under attack. One of the most troubling aspects of space radiation is how little we can do about it with current technology. Unlike other problems in spaceflight, radiation cannot be solved simply with better training or stronger materials. It is a fundamental physical reality of the universe. We can reduce exposure, but we cannot eliminate it. Every solution involves trade-offs that create new problems in cost, weight, and complexity. Perhaps most importantly, radiation damage is often invisible until it is too late. Astronauts may feel fine while their cells accumulate damage over time. By the time symptoms appear, the harm may already be irreversible. This makes radiation one of the most dangerous threats because it undermines health silently and relentlessly. Extreme isolation is not just a social inconvenience for humans. It is a direct challenge to how the human brain and mind are wired to function. Humans evolved as deeply social beings, dependent on constant interaction, shared experiences, and emotional feedback from others. When these elements are removed for long periods, especially in confined and high-risk environments like deep space, the psychological strain can become as dangerous as any physical threat. Long-duration space missions expose humans to a level of isolation that has never been experienced in normal life, and the human mind does not tolerate it well. One of the first psychological effects of extreme isolation is loneliness. Loneliness is not simply the absence of people, it is the absence of meaningful connection. In deep space, astronauts are physically separated from everyone they know, including family, friends, and society itself. Even though they may be surrounded by a small crew, the lack of variety in social interaction becomes emotionally exhausting. Over time, familiar faces can begin to feel oppressive rather than comforting, leading to emotional withdrawal and irritability. Confinement intensifies this problem. Spacecraft and habitats are extremely small, with little privacy. Astronauts cannot step outside to clear their minds or escape tension. Every sound, movement, and habit of others becomes impossible to ignore. Minor annoyances can grow into major conflicts, not because of personality flaws, but because the brain is under constant stress with no outlet. In such conditions, emotional regulation becomes harder, and patience wears thin. Another major psychological strain comes from monotony and sensory deprivation. On Earth, the human brain is constantly stimulated by changing environments, new faces, colors, sounds, and experiences. In extreme isolation, days become repetitive and predictable. The same walls, the same routines, and the same limited visual environment can cause the brain to enter a state of understimulation. This can lead to boredom, reduced motivation, and a sense of meaninglessness, which are powerful contributors to depression. Time perception also changes in isolation. Without natural cues like day-night cycles, social events, or environmental changes, days can blur together. This distortion of time can make long missions feel endless. When people cannot clearly sense progress or milestones, motivation declines. In extreme cases, individuals may begin to feel emotionally detached from the future, focusing only on survival rather than purpose. Stress is constant in isolated, high-risk environments. In space, astronauts are always aware that a single mistake or system failure could be fatal. Unlike on Earth, there is no immediate rescue and no escape. This creates a background level of anxiety that never fully disappears. Over time, chronic stress can impair memory, decision making, and emotional control. It also increases the risk of depression and burnout. Communication delays add another psychological burden. In deep space, messages to Earth can take many minutes to arrive, and replies take just as long to return. This removes real-time conversation, which is essential for emotional support. A person cannot vent, seek reassurance, or receive comfort in the moment they need it. Emotional problems must be handled internally or within the small crew, increasing psychological pressure and the risk of unresolved conflict. Isolation also affects identity and self-perception. On Earth, people define themselves through roles, relationships, and social feedback. In extreme isolation, many of these reference points disappear. Over time, individuals may experience a weakened sense of self or question their purpose. This can lead to emotional numbness, detachment, or a loss of motivation, all of which are dangerous in environments that demand constant alertness and responsibility. Group dynamics are another critical concern. In isolated conditions, small interpersonal tensions can escalate quickly. Misunderstandings linger longer because there are fewer distractions and fewer people to interact with. Power struggles, resentment, and mistrust can develop even among highly trained professionals. Once trust begins to erode, teamwork suffers, and in space, teamwork is essential for survival. Sleep disruption further worsens psychological strain. Isolation, artificial lighting, stress, and lack of natural rhythms interfere with normal sleep patterns. Poor sleep affects mood, attention, emotional stability, and impulse control. Over long periods, Sleep deprivation can amplify anxiety and depression, reduce cognitive performance, and increase the likelihood of mistakes. Another overlooked effect of extreme isolation is emotional suppression. In high-risk missions, individuals may feel pressure to appear strong and composed at all times. Expressing fear, sadness, or frustration may feel unacceptable. Suppressed emotions do not disappear, they accumulate. Over time, this emotional buildup can result in sudden emotional breakdowns or long-term psychological damage. History provides warnings. Studies of people in isolated environments on Earth, such as polar researchers, submariners, and long-term confinement experiments, show increased rates of depression, anxiety, irritability, and cognitive decline. These environments are still far less isolated than deep space, where distance makes help impossible and danger constant. If such effects occur on Earth, they would likely be magnified in space. Perhaps the most dangerous aspect of psychological decline is that it is not always visible. A person may continue performing tasks while internally losing focus, motivation, or emotional stability. In space, delayed recognition of psychological problems can lead to irreversible consequences. A single poor decision, driven by fatigue, stress, or emotional strain, can threaten the entire mission. In extreme isolation, the human mind faces limits just as real as physical ones. While training, discipline, and technology can reduce some risks, they cannot change the fundamental social nature of the human brain. Isolation, confinement, monotony, and distance from Earth slowly erode mental resilience. When missions last months or years, these effects are not temporary challenges but accumulating threats. Extreme isolation does not simply test human psychology. It pushes it beyond the environment it evolved to survive in. Until there is a way to fully protect mental health over long periods without meaningful human connection, psychological limits remain one of the most powerful barriers to deep space travel. Engineering failures and reliability risks are among the most underestimated dangers of long-duration space missions. When humans imagine space travel, they often focus on bold launches and distant destinations, but survival in space depends almost entirely on machines working perfectly for extremely long periods. Unlike on Earth, where systems can be repaired, replaced, or shut down safely, space offers no margin for error. In deep space, engineering is not just about performance. It is about absolute reliability in an environment where failure is unforgiving. Every human space mission depends on complex, interconnected systems. These include life support, power generation, temperature control, propulsion, navigation, communication, and structural integrity. Each system must function continuously, often for years, without external assistance. If even one critical system fails, the consequences can be immediate and fatal. What makes this risk so severe is that no engineered system is ever truly failure-proof. Life support systems are the most critical. Humans cannot survive more than minutes without oxygen, hours without temperature regulation, or days without water. In space, oxygen must be generated or recycled, carbon dioxide removed, water purified, and waste processed. These systems rely on pumps, filters, sensors, valves, and software. Over long durations, components wear out, clog, degrade, or malfunction. Even on the International Space Station, only a few hundred kilometers from Earth, life support failures occur regularly and require constant maintenance and replacement parts. In deep space, replacement is impossible. redundancy is often presented as the solution. Engineers design multiple backup systems so that if one fails, another takes over. However, redundancy has limits. Every backup adds weight, complexity, and new potential failure points. More components mean more things that can break. Over time, redundant systems may fail in similar ways due to shared design flaws or environmental stress, leading to cascading failures where backups fail one after another. Power systems present another major risk. Spacecraft rely on solar panels, batteries, and power management electronics. Solar panels degrade over time due to radiation and micrometeoroid impacts. Batteries lose capacity with repeated charging cycles. Power electronics are sensitive to radiation. Induced errors. A gradual loss of power can disable communication, life support, and navigation simultaneously. In deep space, restoring power may be impossible once critical thresholds are crossed. Thermal control is equally vital and equally fragile. Space is not uniformly cold or hot. It is both. Spacecraft are exposed to intense sunlight on one side and extreme cold on the other. Thermal systems use insulation, radiators, heaters, and fluid loops to keep temperatures within survivable limits. A leak, pump failure, or sensor error can cause overheating or freezing. Electronics can fail, seals can crack, and materials can become brittle. Temperature failure does not just damage equipment, it directly threatens human life. Radiation adds another layer of engineering risk. High-energy particles can damage electronic components, corrupt software, and cause unpredictable behavior in systems. A single radiation strike can flip bits in memory, trigger false sensor readings, or shut down critical computers. Engineers use radiation, hardened components, but these are slower, heavier, and still not immune. Over long missions, cumulative radiation damage increases the chance of sudden, unexplained failures. Software reliability is a hidden but serious concern. Modern spacecraft are controlled by millions of lines of code. Software bugs are inevitable in systems of this complexity. On Earth, software can be patched, updated, and debugged continuously. In deep space, software updates are risky, delayed, and limited by communication constraints. A minor coding error, timing glitch, or unexpected interaction between systems can cause catastrophic outcomes. History shows that software errors have already caused the loss of spacecraft without any hardware failure at all. Mechanical wear is unavoidable. Moving parts, such as motors, bearings, pumps, and joints, degrade over time. Lubricants behave differently in vacuum and extreme temperatures. Dust, vibration, and repeated stress weaken components. On long missions, mechanical systems must operate far beyond their original design lifetimes. Once a critical mechanical part fails, there may be no way to repair or replace it with the tools and materials available on board. Structural integrity is also at risk. Spacecraft structures must survive launch stresses, temperature cycling, radiation, and micrometeoroid impacts. Tiny impacts at extremely high speeds can puncture surfaces, damage wiring, or weaken pressure vessels. Even small cracks can grow over time due to repeated stress. A slow air leak may not be immediately noticeable, but can become fatal if undetected. One of the most dangerous aspects of engineering failure in deep space is the lack of rescue. On Earth, engineering failures are often survivable because help is nearby. In low Earth orbit, astronauts can return home within hours. In deep space, failure is final. Engineers must assume that crews will be completely alone, with no external assistance, for years. This raises reliability requirements far beyond anything ever achieved in human engineering. Human interaction with machines also introduces risk. Astronauts under stress, fatigue, and psychological strain may make mistakes when operating or repairing systems. Procedures that are safe on Earth may become dangerous in microgravity or emergency conditions. A single incorrect action can damage equipment beyond repair. Perhaps the greatest challenge is that long-duration missions combine all these risks simultaneously. Systems must survive time, radiation, isolation, and human error all at once. Failures are not isolated events. They interact and cascade. A power issue can disable thermal control, which damages electronics, which disrupts life support. Engineering systems are tightly linked, meaning one failure can trigger many others. Economics, energy, and political reality form a powerful trio of constraints that shape what humanity can realistically achieve in space. While science fiction and ambitious announcements often portray interplanetary travel as an inevitable future, the real-world forces of money, energy limits, and politics tell a very different story. These factors do not operate independently. They are deeply connected, and together they impose boundaries that are just as restrictive as physics or biology. At the most basic level, space exploration is extremely expensive. Every kilogram launched into space costs a tremendous amount of money, even with modern reusable rockets. A human mission to Mars would require not just one launch, but many carrying spacecraft components, fuel, supplies, life support systems, and emergency backups. The cost quickly rises into the hundreds of billions, if not trillions, of dollars. These are not one-time expenses. Long-term missions require decades of funding for research, testing, training, and continuous support. Economic reality forces societies to make choices. Governments must decide how to allocate limited resources among healthcare, education, infrastructure, defense, climate response, and social welfare. Space exploration competes with urgent problems that affect millions of people immediately. When economic downturns occur, space budgets are often among the first to be reduced or delayed. History shows this clearly. Many ambitious space plans have been canceled or scaled back when political priorities changed or financial pressures increased. Energy is another fundamental limitation. Space travel is not just costly in money, it is costly in energy. Launching a spacecraft requires enormous amounts of fuel to overcome Earth's gravity. Traveling to Mars requires even more energy, not just for propulsion, but also for life support, radiation shielding, temperature control, communication, and return travel. Every system that keeps humans alive in space consumes power continuously. On Earth, energy can be generated from many sources and distributed through vast networks. In space, energy generation is limited and fragile. Solar power weakens with distance from the sun and can be disrupted by dust, damage, or orientation issues. Nuclear power offers higher output, but introduces political, safety, and engineering challenges. Any energy system must operate reliably for years without maintenance or replacement, a requirement that pushes technology to its limits. The energy cost of sustaining human life is often underestimated. Humans are inefficient passengers. They require oxygen, water, food, temperature regulation, and waste management. All of this requires energy. Robots, by contrast, need far less energy and no life support systems. From an economic and energetic perspective, robotic exploration delivers far more scientific return per unit of cost and power. This makes human missions difficult to justify when compared to automated alternatives. Political reality adds another layer of complexity. Large-scale space missions depend almost entirely on government support. Unlike commercial ventures, there is no immediate financial return from sending humans to Mars. This means missions must survive election cycles, leadership changes, and shifting national priorities. A project that requires 20 or 30 years of continuous commitment may span multiple governments with different ideologies and goals. International cooperation is often proposed as a solution, but it brings its own challenges. Coordinating funding, technology, and decision-making among multiple countries is slow and politically sensitive. Conflicts, sanctions, and diplomatic breakdowns can disrupt cooperation overnight. A mission as complex as a Mars expedition cannot tolerate long interruptions or uncertainty, yet political systems are inherently unstable. Public support is also critical, and it is fragile. Space exploration captures imagination during moments of success, but quickly loses attention when results are slow or abstract. As costs rise and timelines extend, public enthusiasm often fades. Without strong public backing, politicians have little incentive to continue funding expensive programs with no immediate benefit to voters. There is also the issue of opportunity cost. Money and energy invested in a Mars mission are resources not invested elsewhere. This raises ethical questions. Should vast sums be spent sending a few humans to another planet, while billions on Earth face poverty, health crises, and environmental threats? Different societies answer this question differently, but it remains a powerful argument against large-scale human space colonization. Private companies have entered the space conversation, but they do not escape economic reality. Even the wealthiest corporations rely on government contracts, subsidies, and regulatory approval. Their long-term plans are vulnerable to market changes, investor confidence, and legal constraints. Commercial interest does not eliminate the enormous energy and cost requirements. It only redistributes them. Energy and economics also affect sustainability. A Mars mission is not just about getting there once. True human presence would require ongoing resupply, infrastructure, and protection. Each additional mission multiplies costs and energy demands. Without a self-sustaining system which is far beyond current capability, human presence remains dependent on Earth, making it economically fragile and politically vulnerable. Perhaps most importantly, economics and politics operate on human time scales, not cosmic ones. Budgets are annual. Governments think in terms of years, not decades. Space exploration on the scale required for Mars demands long-term stability in funding and leadership that human societies rarely maintain. This mismatch between ambition and reality has repeatedly stalled grand space visions. In the end, economics, energy, and political reality act as invisible gravity, pulling ambitious dreams back toward Earth. They do not make space exploration impossible, but they impose limits that cannot be ignored. Without overwhelming economic justification, revolutionary energy breakthroughs, and unprecedented political stability, large-scale human missions beyond Earth remain more symbolic than practical. These realities remind us that reaching for the stars is not just a scientific challenge. It is a societal one. Mars is often described as Earth's neighbor, or a potential second home, but this language hides a harsh reality. Mars is not a welcoming world waiting to be settled. It is an environment that actively works against human survival at nearly every level. From its atmosphere and temperature to its soil and radiation exposure, Mars is fundamentally hostile to human life. Surviving there would require constant technological intervention, and even then, the risks would remain extreme. The most immediate problem is Mars's atmosphere. It is incredibly thin, about 1% as dense as Earth's atmosphere, and composed mostly of carbon dioxide. Humans cannot breathe it, and it provides almost no protection from radiation or meteoroids. On Earth, atmospheric pressure keeps oxygen dissolved in our blood and protects our bodies from boiling fluids. On Mars, the pressure is so low that unprotected human exposure would cause severe injury within seconds. Simply stepping outside without a suit would be fatal. Temperature is another deadly factor. Mars is cold, far colder than most places on Earth. Average surface temperatures hover around -60 degrees Celsius, and in some regions they drop much lower. These temperatures can freeze human tissue quickly and make equipment brittle and unreliable. Unlike Earth, Mars lacks oceans and a thick atmosphere to store and distribute heat, so temperature swings between day and night are extreme. Human habitats would need constant heating, consuming large amounts of energy and introducing more points of failure. Radiation on Mars is a continuous threat. Unlike Earth, Mars has no strong magnetic field to deflect cosmic radiation, and its thin atmosphere offers little shielding. As a result, the surface is bombarded with high-energy particles from space. Long-term exposure increases the risk of cancer, damages the nervous system, and harms vital organs. Living on the surface would expose humans to radiation levels far above safe limits, making extended stays extremely dangerous. Mars's soil presents another hidden danger. It contains toxic chemicals that are harmful to humans. These substances can interfere with thyroid function and damage internal organs if inhaled or ingested. The fine dust on Mars is easily stirred by wind and can cling to surfaces, including spacesuits and equipment. Over time, this dust could infiltrate habitats, contaminate air systems, and pose serious health risks. Water, essential for life, is not easily accessible on Mars. While there is evidence of ice and frozen water beneath the surface, extracting and purifying it requires heavy machinery, energy, and time. There are no flowing rivers or accessible lakes. Any water system would need to be carefully managed, recycled, and protected from contamination. A failure in water processing would be catastrophic, as resupply from Earth is impractical. Food production on Mars is another major challenge. Mars lacks fertile soil, a stable climate, and natural ecosystems. Growing food would require sealed environments, artificial lighting, and carefully controlled conditions. Plants would need protection from radiation and dust, and nutrient supply would need to be manufactured or imported. Even small failures in these systems could lead to food shortages that threaten survival. Gravity on Mars is only about 38% of Earth's gravity. While this might sound manageable, the long-term effects on the human body are unknown. Extended exposure to reduced gravity could weaken bones and muscles, impair circulation, and affect organ function. Humans arriving on Mars after months in microgravity would already be physically weakened, and Mars's low gravity may not be sufficient to restore their health. Dust storms add another layer of danger. Mars is known for massive dust storms that can cover the entire planet and last for weeks or months. These storms reduce sunlight, cutting off solar power, and coat equipment with fine dust that can damage moving parts and electronics. Unlike Earth storms, there is little moisture to settle the dust, allowing it to remain suspended for long periods. Isolation intensifies Mars's hostility. Mars is months away from Earth, making rescue impossible and communication delayed. In emergencies, astronauts cannot rely on immediate assistance. Every problem must be solved locally, under stress, with limited resources. This isolation turns Mars from a challenging environment into a potentially lethal one. Perhaps the most important point is that Mars does not forgive mistakes. On Earth, the environment supports life naturally. If technology fails, humans can often survive long enough to recover or adapt. On Mars, technology is life. Every breath, every sip of water, and every moment of warmth depends on machines functioning perfectly. A small error, leak, or malfunction can quickly escalate into a fatal situation. Mars also lacks many of the protective systems that make Earth habitable. There is no thick atmosphere to burn up meteoroids, no global magnetic field to shield radiation, and no biosphere to recycle waste naturally. Humans must recreate all of these systems artificially, at enormous cost and risk. In the end, Mars is not hostile because it is evil or mysterious. It is hostile because it is fundamentally different from Earth. It does not support human biology, and it offers no natural safety net. Surviving on Mars would mean living inside fragile technological bubbles, constantly fighting an environment that never stops trying to kill you. Calling Mars a future home oversimplifies the reality. It is a world where survival is possible only with extreme effort and constant vigilance, and even then, it is never guaranteed. Mars is not a new Earth. It is a reminder of how rare and fragile life truly is.